Suppose that we have a semiconductor connected to an external battery as shown in the figure. This battery will result in a current which will be flowing in the positive x direction. In this lecture, the orientation of axes is very important, so be careful with them. Now, we introduce a transverse magnetic field effective on the whole semiconductor uniformly with the direction as shown. Magnetic flux density is in the direction of plus z axis and current is in the direction of plus x axis. The moving charge carriers will experience force, and the force due to magnetic field is equal to charge multiplied by vector product of velocity of charged particles and magnetic flux density. Now we can have two cases here. Either the semiconductor is of p-type or n-type. First we take p-type semiconductor. Here we are going to focus on the front view of the semiconductor, which is this portion. We know that the current is in the positive x direction. Now, since it is a p-type, holes will be the majority charge carriers and holes will be moving in the direction same as that of the electric current. Now, we are going to find effective force on holes due to the magnetic field. Force is equal to. Now we are only interested to find the direction in which the force will be exerted. The direction vector of force will be equal to, we know unit velocity vector of holes will be x cap, and the direction vector for magnetic flux density is plus z cap, and this vector product will result in minus y cap. It means that holes will move in the negative z direction and will follow a path similar to as shown. Now we will analyze for n-type semiconductor. The current will remain in the x direction, but we know that electrons move opposite to the flow of electric current. Therefore, electron will move in the negative x direction. Force on charged particles due to magnetic field is equal to minus q multiplied by vector product of velocity vector and magnetic flux density. The reason why we are having minus charge because electrons have negative charge, and the formula for force contains absolute charge on the particle. Here also we will find the direction in which charge carriers will experience force and will get accumulated. Minus sign we are taking from the charge velocity vector, which is minus x cap. Direction vector of magnetic flux density is z cap. Two negative signs will cancel each other. Therefore, the direction vector of force will come out to be x cap vector product with z cap. Direction vector of force in n-type semiconductor comes out to be negative y cap. So, electrons will also experience force in the negative y direction and will move similar to as shown in the figure. So, you can observe that irrespective of the type of semiconductor, the charge carriers move in negative y direction and upon accumulation will create an electric field in the y axis. Remember that we will have actually two electric fields. One is due to the presence of external battery, and the direction of this electric field will be in x direction. Similarly, we will have another electric field which is caused due to magnetic flux density and will be in y direction. Due to this electric field, a potential called Hall voltage appears between the two surfaces in y axis. Suppose that we are going to attach a voltmeter between the two surfaces in the y direction for both type of semiconductors. You see that for p-type semiconductor, holes will get accumulated on the bottom surface in the y-axis. Therefore, if we measure the voltage with positive node on the top surface, then we will get the voltage to be a negative value. And here for n-type semiconductor, electrons will get accumulated on the bottom surface, and again if we try to find the Hall voltage with a voltmeter with positive node on the top surface, then we will get a positive Hall voltage. And this is the main principle by which we can define whether the semiconductor is n-type or p-type experimentally, as by applying the same magnetic field, if we find the Hall voltage to be negative, then the semiconductor is p-type, and if we find the Hall voltage positive, then the semiconductor is of n-type. This is not a point that you should learn, because if we change the polarity of the voltmeter, then we will get the opposite result. You have to understand the phenomena, and you should understand the direction in which the charge carriers are getting accumulated. Now the question is, will the charge carriers keep accumulating on the bottom surface? The answer is no. The charge carriers will keep accumulating until steady state situation, which will be achieved when the force due to magnetic flux density will be exactly equal to the force due to the electric field which is caused due to the accumulation of charge carriers and will be in the y direction. To derive few important relations, we have to introduce few more parameters in this semiconductor crystal. We will assume that the length of the semiconductor is x, the width of the semiconductor is w, and depth of the semiconductor is d. In steady state, the net force on the charged particle will be 0, and the force is caused due to electric field and magnetic field. Force due to electric field is equal to QE, whereas force due to magnetic field is equal to Q into V cross V. By neglecting the charge, we can write electric field is equal to V cross V. Now, this is the exact expression. But from now, we will not focus on the direction, we are going to focus only on the magnitude of the parameters. Again, this is the front view of the semiconductor. This will be x direction and this will be y direction. Suppose that if we have a charge carrier, then in either case, force due to magnetic field will be in the negative y direction, and the force which is caused due to the accumulation of charge carriers will be in this direction. Also, we know that this internal electric field which is caused due to the accumulation of charge carriers results in a Hall voltage which is represented by Vh and will be in the y direction. We know that the electric field is equal to Hall voltage divided by distance d. You can observe that this is equal to d, as can be observed in the other graph, and this is equal to x. As I told you earlier, we are focused only on the magnitude of the values. We are not focusing on the direction. So, by equating these two equations, we will get Hall voltage divided by d to be equal to V into V. Now, I hope that you can recall what is V. V is the velocity of the charge carriers, we all know, but in terms of semiconductor, it is also given another name which you have already studied. This is nothing but the drift velocity. And you know that drift current density is equal to drift velocity multiplied by charge multiplied by charge carrier concentration. Here, C is representing charge carrier concentration. Also, we know that current density is actually equal to current divided by area. Since the current is in the x direction, we will introduce a suffix x, and also area in the x direction is d into w, where d is the depth and w is the width. Now equating these two values of drift current density, we will get drift velocity multiplied by charge multiplied by carrier concentration equal to current in the x direction divided by d into w. It will give drift velocity to be equal to current divided by charge into carrier concentration into depth into width. Now we will put this value of drift velocity in the Hall voltage equation. Then we will get this d will cancel, and we have the magnitude of Hall voltage to be equal to magnetic flux density multiplied by current divided by width of the semiconductor into the charge on a charge carrier multiplied by charge carrier concentration. And by this formula we can find magnitude of Hall voltage. We have ignored the directions, so we are going to find only the magnitude. The direction, whether it is going to be positive or negative, you have to find it on your own. One way is to simply analyze yourself as I have described earlier, or the other way is that you have to strictly follow the directions in the derivation. The parameters which are different for p-type and n-type semiconductor are the direction of induced electric field and the velocity of the charge carriers. Both these parameters will have different directions in different semiconductors, but you can find the magnitude for either type of semiconductor by this formula. One more important thing is charge multiplied by charge carrier concentration is sometimes referred to as charge density, and this will change the formula for Hall voltage to be like this. You learned that we have Hall voltage Vh. There is another parameter which is called Hall coefficient, which we will represent it by Hc, and the Hall coefficient is defined by 1 upon charge density, and from this equation we will get 1 upon charge density to be equal to, therefore the Hall coefficient will be equal to Hall voltage multiplied by width of the semiconductor divided by magnetic flux density into current. And suppose that, like the way we were finding the Hall voltage, we are also interested in finding the mobility, then the conductivity is measured together with Hall coefficient. The mobility can be determined from the formula mobility is equal to conductivity multiplied by Hall coefficient. So, by using this formula, if the conductivity is also measured together with the Hall coefficient, we can find the mobility of the charge carriers also. So you see that it is one of the experiments through which the mobility of charge carriers is actually determined. We strictly follow that every charge carrier moves with mean drift velocity. But if we assume that the current carriers have random thermal distribution in speed, then the formula for Hall coefficient changes slightly and will equal to 3 pi divided by 8 rho. Which will change the formula for mobility also.